Welcome to the deep dive.
Glad to be here.
And if you are tuning in right now, you are exactly our favorite kind of listener. You're the naturally curious learner.
Exactly.
You're probably juggling a million things today, but you still want a really thorough, accessible breakdown of the technology that is actually shaping the future.
And you definitely don't want to drown in information overload.
No, nobody wants that. So we have a very specific mission for you today. We're decoding this massive 120-minute curriculum document. It's called Module 5, Soroban Smart Contracts.
Which is part of the Vibe Code blockchain course.
Right. That's the source material.
Yep.
And our ultimate goal today is to help you make this major conceptual transition.
Yeah, if you've been following along with this space, you likely already understand how to execute basic blockchain operations.
Basics.
Right. The mechanics of sending payments, issuing digital assets, making offers on a ledger. We've covered that. But today, we're crossing the threshold into the world of programmable logic.
Programmable logic, meaning smart contracts.
Yes. The actual code that runs autonomously on a decentralized network.
Which brings us to our key context for today's discussion. Soroban.
The Soroban network.
Right, which is Stellar's smart contract platform that officially launched in 2024. But here is the massive hurdle that the source document introduces right away.
Oh, yeah. The language barrier.
Exactly. These contracts are written in a programming language called Rust, and then they're compiled into an environment called WebAssembly, or Wasm for short.
Wasm.
Okay, let's unpack this, because for a lot of people, just hearing the words Rust and WebAssembly in the same sentence is enough to make them, close their laptops and just walk away.
It sounds incredibly intimidating.
It sounds like a brick wall for anyone who isn't already a senior software engineer.
It absolutely does.
Yeah.
But the curriculum introduces an incredible twist right off the bat. And this should immediately put your mind at ease. You will not need deep textbook Rust expertise today.
Not at all.
In fact, you might not ever need to write a single line of Rust from scratch.
Which is wild.
It is. This entire module is built around a concept called vibe coding.
Vibe coding, I love that term.
It's great. You will be utilizing an AI coding partner named Claude Code. You simply describe what you want your smart contract to do in plain English, and the AI writes the Rust code for you.
So your job shifts.
Dramatically.
Yeah.
You go from being a manual syntax coder, typing out every bracket, to acting as an editor and a logic verifier.
Okay, hold on. I need to push back on this for a second.
Sure.
You want me to just trust an AI chatbot to write code that potentially holds real, actual money? Isn't that a recipe for a massive financial hack? I mean, we've all seen AI make silly mistakes.
Oh, absolutely. That is exactly the right kind of skepticism to have. And it's a question the source material completely anticipates.
So what's the answer?
The short answer is no, you don't blindly trust it. But the reason this pairing works so well is because of the strict rules of the environment the AI is writing for. You have a built-in safety net.
A safety net.
Yes. The AI generates the code, but before it ever touches a live network, it has to pass through the incredibly unforgiving rules of the Rust compiler and the Soroban sandbox.
Okay.
The strict environment is what keeps the AI in check. It simply won't let bad syntax through.
I see. So the environment itself is kind of like the bouncer at the door.
Exactly.
So before we get into exactly how the AI does this, we need to understand that playing field. The source document lays out a really clear comparison between Soroban and the current heavyweight in the smart contract space.
Ethereum.
Ethereum, right. Let's look at that table from the source. Ethereum uses a language called Solidity. It runs on the Ethereum virtual machine, or EVM, and it is infamous for having variable gas fees.
Right.
For a user, that means you never quite know what a transaction will cost until you try to execute it.
It fluctuates.
Exactly. Now, Soroban, on the other hand, uses Rust. It runs on WebAssembly, and it has predictable, pre-calculated gas fees. You know the exact cost before you ever hit the button.
What's fascinating here is exactly why the creators of Soroban chose Rust instead of just copying Ethereum's approach.
Because copying it would have been much easier. Really.
Oh, way easier. But Rust has a famously strict ownership model when it comes to managing a computer's memory. Now, without getting bogged down in computer science jargon, this ownership model physically prevents entire classes of bugs from ever existing.
It stops them entirely.
It catches them at compile time, meaning the moment you try to build the code before it can even run on the network.
What kind of bugs are we talking about here?
We are talking about critical vulnerabilities that have plagued older programming languages for decades. For example, Null pointers.
Null pointers.
Imagine a treasure map that points to a set of coordinates, but when you get there, the island simply doesn't exist.
Right.
The program crashes trying to find it. Rust won't let you compile a map without a verified island.
Okay, that makes sense.
Then you have buffer overflows, which is the equivalent of trying to forcefully pour 10 gallons of water into a 5-gallon bucket. It causes data to spill over and corrupt other parts of the system.
And Rust stops that.
Yes, Rust's compiler checks the bucket size first. It also stops use after free errors.
Use after free? What is that?
Think of that like trying to use a hotel room key days after you've already checked out and the room has been given to someone else. Rust physically revokes the key the moment you check out.
Wow. So it forces you to be disciplined before the code ever goes live. And the source points out another massive game changer for security here: re-entrancy risk.
Yes, this is a big one.
The curriculum notes that in Ethereum, developers have to manually write defenses against re-entrancy attacks. How does that vulnerability actually work in practice?
A re-entrancy attack is essentially a digital heist based on speed and interruption. Imagine a thief goes to a bank teller and asks to withdraw their $100 balance. The teller hands over the cash. But before the teller can update the ledger to show the balance is now zero, the thief distracts them and says, "Wait, I'd like to withdraw my $100 balance again."
Because the ledger hasn't been updated yet.
Exactly. The teller hands over another $100. In the blockchain world, a malicious contract repeatedly calls back into the original contract, draining funds before the first transaction fully completes.
And that's a real problem.
Historically, this exact type of loophole has caused multi-million-dollar hacks in other ecosystems.
And how does Soroban fix that? Does it just give you better tools to defend against it?
No, it goes much further than that. In Soroban, re-entrancy is simply impossible by design.
Impossible.
Cross-contract calls have to fully complete and resolve before the execution is allowed to resume. The network physically won't allow the thief to ask for a second withdrawal until the teller has finished writing the new zero balance in the ledger.
That is a huge relief. So bringing this back to our workflow as a learner, because Rust has this incredibly steep learning curve, but its security rules are practically bulletproof. Using an AI like Claude Code is the perfect pairing.
It really is.
The AI knows how to navigate the strict rules to generate the correct, idiomatic Rust code from your plain English descriptions. And the Rust compiler acts as the ultimate quality assurance test.
Precisely. The AI acts as your architect, drawing up the blueprints, but the Rust compiler is the safety inspector that refuses to approve the building if a single beam is out of place.
That's a great way to look at it. Let's actually walk through what building that first structure looks like. The curriculum sets the stage with the classic "Hello World" of Soroban.
The starting line for every developer.
Right. But to even get there, you need a development environment. Usually, setting up a coding environment is an absolute nightmare of downloading dependencies and fixing path errors. How does the module handle this?
It leans entirely into the vibe coding philosophy. You literally just open Claude Code and prompt it to write a bash setup script for macOS.
You don't even write the setup script yourself.
Nope. The AI generates a script that you run in your terminal, and it installs everything automatically. The key technical tools it pulls in are RustUp, which manages your Rust installation, and the Stellar client, which is your command line interface for interacting with the network.
The document also highlights a very specific technical requirement during the setup. It says you must specifically add something called the WebAssembly target package. It's listed as was M32 unknown. Why do we need that?
Think of it like packing a suitcase for a very specific climate. When you normally write code on a Mac, the compiler packs the instructions in a way that macOS understands.
Right.
But we aren't running this code on your Mac. We are deploying it to the decentralized Soroban network, which uses WebAssembly. So adding that specific target package tells the compiler, hey, translate all of this logic into the exact dialect that the WebAssembly sandbox requires.
Okay, so the environment is set up. The AI generates a basic Hello World contract. For someone looking at this code for the first time, what are the actual visual landmarks they should be looking for? How do we read this without getting lost in the syntax?
Even if you are not a programmer, the anatomy of a Soroban contract is highly structured and easy to read once you know the core patterns. At the very top of the file, the AI will add a specific label that indicates no standard library is being used. It's literally #!no_STD.
Why strip away the standard library?
Because the WebAssembly sandbox environment is incredibly lightweight and isolated. It doesn't have or need access to standard operating system features like writing files to a hard drive or managing a monitor display.
So you don't need all that extra code.
Exactly. Stripping out the standard library is like packing an ultralight backpack for a sprint. You leave all the heavy, unnecessary camping gear behind.
That makes sense. Keep it self-contained. What else are we looking for in the code?
Next, you will see specific contract labels attached to sections of the code. Things like bracket contract bracket and bracket contract temple bracket. The AI adds these to act like name tags.
Name tags for the network.
Yes. One label tells the network this entire block of code is the deployable contract. Another label sits right above specific functions to announce this specific action is publicly callable by outside users.
And the source mentions a crucial component called the env, or environment variable. It seems to be passed into almost every single function the AI writes. What is the env doing?
The end is arguably the most important concept in Soroban. You can think of the end as the contract's passport to the outside world.
A passport?
Because the contract lives inside that highly restricted sandbox we just talked about, you can't just freely grab data. The end passport is what grants the code permission to access persistent storage, allows it to publish public events to the ledger, and lets it read current ledger information like timestamps.
It's brilliant how structured it is. Now that we understand the anatomy, here's where it gets really interesting.
Oh, yeah.
The curriculum doesn't just stop at Hello World. It has you build 3 real-world smart contracts using AI prompts. The first one is a counter contract.
A classic example.
Right. You tell Claude to build a contract that stores a numeric count. It has an increment function to increase it, a get function to read it, and a reset function to put it back to 0. But obviously, you don't want just anyone on the internet resetting your counter. How does the AI ensure that a random user can't just hit the reset button?
The AI implements a strict administrative check. When the contract is first initialized, it stores the admin's identity, their public key, in the contract's instance storage.
Oh, okay.
Then, inside the reset function, the AI explicitly writes a command requiring the caller's authentication. It's usually something like admin.require_auth.
And what does that actually do?
By calling that authentication function, the Soroban network physically checks that the person trying to reset the counter has actually cryptographically signed the transaction with the admin's secret key. If the signature doesn't match, the network rejects the transaction before the code even tries to run.
So as the human verifier, my job is just to look at the code Claude generated and make sure I see that require offline before the reset logic happens.
Exactly. You are verifying the logic, not typing out the cryptography. And the AI also includes a command using that env passport we talked about to publish an event. It calls env.events.publish. So every time the counter goes up, it emits a public record to the ledger, creating a transparent trail of activity.
Let's move to the second contract, because this is where the financial utility really shines. An escrow system.
This is a great use case.
Imagine you are hiring a freelance developer to build a website. You don't want to pay them up front before the work is done, but they don't want to do the work unless they know the money is secure.
Right, a classic trust problem.
So you put $5,000 in a digital escrow. The initial setup requires a depositor, a recipient, an arbiter who can settle disputes, and a specific amount of funds. How does the AI manage the status of that $5,000 safely?
This is a perfect example of state management. The AI uses something called an enum, which is short for enumeration, to track the exact status of the funds.
An enum.
Think of an enum like the gear shift in a car. You could be in park, drive, or reverse. You cannot be in some weird, undefined state halfway between park and drive.
That would break the transmission.
Exactly. The escrow contract strictly defines the state of the funds as either pending, released, or refunded. There is no middle ground where the money just vanishes into the ether.
And how do the funds actually move when the work is done?
The depositor puts the funds in, locking the state to pending. But only the arbiter has the power to change that gear. The arbiter's function uses that same cryptographic authentication check we saw on the counter.
The require auth function.
Yes. If the work is good, the arbiter authenticates and calls a release function to shift the state to released. If the work is terrible, they call a refund function to shift it to refunded. And to actually move the money, the contract utilizes a built-in tool called a token client to securely transfer the native stellar currency between the accounts.
It is quite literally an incorruptible digital lawyer.
It really is.
The third contract the source covers is a voting system. Say we were running a local election. You prompt the AI to initialize a list of candidates, an election deadline, and an admin. But in any election, the biggest threat is someone voting twice. How does the code stop double voting?
The genius of this voting contract is how it leverages persistent storage to enforce the rules of engagement. When you cast your vote, the contract takes your public address and permanently logs it into the network storage.
So it remembers you.
Yes. If you try to submit a second vote, the contract checks the storage, sees your address is already on the ledger, and flat out rejects the transaction.
What about the election deadline? How does a piece of code know what time it is?
It uses the end passport again. It calls nv.ledger.sequence to check the current sequence number of the ledger.
The sequence number.
Yes. The Stellar network produces a new ledger roughly every 5 seconds. The deadline is set to a specific future ledger number. But my favorite part of the AI's logic is how it handles the results. It features a specific function to declare the winner.
Okay, the winner function.
If someone tries to call that winner function before the deadline ledger has passed, the contract is programmed to panic.
Panic? That sounds bad.
In Rust, panicking is actually a good thing. It is a safe, controlled way of halting execution immediately when an impossible or illegal condition is met.
So it just stops.
The program stops, rolls back any changes, and spits out a helpful error message explaining that the election is still ongoing. It refuses to proceed.
It is incredibly elegant. But you mentioned persistent storage just now when talking about the voter addresses. The source material actually dedicates a whole section to a deep dive into storage.
It's a vital topic.
Soroban doesn't just have one big, messy bucket for all its data. It has 3 distinct storage tiers. Where does all this data actually live, and why does it matter?
Choosing the right storage tier is critical because it directly impacts both the financial costs of running your decentralized app and its overall reliability.
Cost and reliability.
Yes. The 3 tiers serve very different purposes. First, you have instance storage. This is meant for lightweight data that shares the lifetime of the contract itself.
Like what?
Think of the admin configurations we saw in the counter and escrow examples. As long as the contract exists, that admin data exists.
What about the massive lists of data like our voter deduplication list or user account balances?
That goes into persistent storage. This is the heavy-duty tier used for critical user data. But here's the catch. Persistent storage is rent-based.
Rent-based, meaning you have to pay for it.
You actually have to pay fees to keep that data alive on the network. This economic model ensures that the global ledger does not get permanently bloated with abandoned, useless data. If you stop paying rent, the data gets archived.
And the 3rd tier.
Finally, there is temporary storage. This data automatically expires after a short period. It is absolutely perfect for things like rate-limiting locks or temporary calculations where you don't need a permanent historical record, saving you a ton of money on rent.
Okay, so we have conceptually designed the contract. We have verified the AI's logic, chosen the right storage, and deployed it to the network. But let's pause and think about the user experience.
The front end.
Right. My grandma isn't going to open up a command line terminal to vote in a local election or release funds to a freelancer. How do actual human beings interact with this bulletproof code we just built?
That is the crucial bridge. To build an app that everyday people can use, you need a web interface. The curriculum transitions into showing you how to call these smart contracts to a JavaScript environment, specifically using a Node.js application and a library called the Stellar SDK.
And when you are building that bridge between the web app and the Soroban network, the module highlights one non-negotiable step. It labels this as the absolute critical rule for JavaScript integration.
Yes, the simulation rule.
A developer must always, without exception, use a function called simulateTransaction before actually submitting the final call to the network. Why is that simulation so important? Why not just send the transaction?
Because skipping the simulation leads to terrible user experiences and wasted money. Running a simulation gives you 2 massive benefits. First, it calculates the exact, predictable gas fee required based on the contract's complexity.
So no surprises.
Exactly.
Yeah.
This means your web interface can show the user exactly what they're going to pay, down to the fractions of cent, before they confirm.
And the second benefit?
It acts as a dry run. It executes the logic against the current state of the ledger without actually changing anything. It validates that the call will succeed.
But if it's going to fail, you know beforehand.
Yes. If the simulation fails, say a user is trying to call the voting winner function before the deadline, which triggers that panic we discussed, you catch the error instantly. The simulation fails, your web app reads the error message, and you can display a nice pop-up to the user saying, "Election's still ongoing," all without the user spending a single cent on failed network fees.
That makes total sense. Dry run everything to save money and frustration. Speaking of dry runs and safety nets, the source wraps up with a major section on testing and security. The curriculum points out that unlike Ethereum, which usually forces developers to rely on complex external frameworks to test their code, Soroban has testing capabilities built directly into its native software development kit.
Yes, the SDK provides tools, specifically Soroban_SDK:/test-tools, to easily mock up fake user addresses and simulate cryptographic signatures. This allows you to thoroughly test your logic locally.
So you don't even need the live network to test it.
Exactly. But this raises an important point about your role as the vibe coder. Even if an AI writes the code, and even if the Rust compiler checks it, you are still the human in the loop.
You're the final sign-off.
Yes. The curriculum provides a fantastic pre-mainnet security checklist that you must manually verify before deploying anything to the real public network.
So we don't just blindly deploy. What exactly are we looking for in this checklist?
First, you must verify authentication. Are all state-changing functions properly protected? You should literally read through the code and ensure you see $require_auth on anything that alters data.
Check. What's next?
Second, you have to verify that the integer arithmetic is safe. In Rust, you should look for specific safe mathematical methods, like .checked_add and .checked_sub.
Why do we need those?
They prevent numbers from silently overflowing their maximum limits and causing catastrophic accounting errors.
Got it. What else is on the checklist?
The checklist also reminds you to double-check your storage choices. Did you accidentally put temporary data in persistent storage and cost yourself a fortune in rent? You have to verify that your JavaScript client argument types match the Rust contract signatures perfectly.
Meaning if they don't match, it breaks.
Right. If your contract expects a 32-bit integer, your web app better be sending a 32-bit integer or the transaction will fail. And finally, you have to ensure that your admin keys are set immutably during the initialization phase, usually locked safely in instant storage.
It is a very comprehensive checklist. But did you notice what is noticeably missing from it?
Re-entrancy checks.
Exactly. Why aren't we checking for re-entrancy?
Because, as we discussed earlier, the Soroban environment handles that massive threat for you natively. You don't have to check for it because it simply cannot happen.
So what does this all mean? Let's bring this all together for you. What you have uncovered today is the immense practical value of vibe coding.
It really is a game changer.
By combining the bulletproof safety of the Rust programming language and Soroban's strictly sandboxed environment with the rapid generation capabilities of AI tools like Claude Code, you can build secure, predictable financial logic without feeling overwhelmed by complex syntax.
You get the safety of a heavily guarded fortress, but you have an AI architect drawing up the exact blueprints for you. Your job is just to review the checklist.
And the source document teases that Module 6 is going to take all of these conceptual pieces and build a complete, full-stack decentralized application, bringing together the smart contract, a front-end interface, and a wallet connection.
If we connect this to the bigger picture, it really makes you rethink the entire future of software development.
How so?
If platforms like Soroban are completely eliminating entire classes of security risks by their very design, and if AI coding partners can consistently generate correct, idiomatic, compile error-free Rust code just from your plain English descriptions, how much of the traditional smart contract developer role will soon just be an exercise in writing precise English instructions rather than writing code at all?
That is a fascinating shift. We are moving away from the era of writing syntax and entering the era of designing pure logic.
Precisely.
It really is a massive paradigm shift. The barrier to entry has never been lower, and the baseline security has never been higher. We hope this deep dive helped you demystify the mechanics of smart contracts and showed you just how accessible this cutting-edge technology is becoming. Thanks for joining us, and keep learning.